Okay, it's a pretty good time to get started. Welcome back to class, everybody. So just to briefly review what we talked about last time, we spent a good fraction of the class talking about homework 3. So you saw how I implemented at least the various parabola classes in my stochastic gradient descent class. And I know that most of you hadn't done the homework at that time, but I've since looked and most of you have turned it in. So hopefully everybody got it to work in a reasonable way where you're satisfied with it. So then we spent the rest of class talking about parallel computing in Python. So you learned about the IPython parallel interface, how you can start a cluster which involves a bunch of engines and a controller, how you can connect a client to that controller. And then we learned about two different ways of interacting with the engine. So one was a direct view, where you could say this engine should receive this particular command to execute. And the other was a load balanced view, where you just say, I need this executed, and the controller is going to pick which is the engine that's working the least, and that's the one that's going to execute that command, okay? And in the next homework assignment, towards the end, you're going to be using the IPython parallel interface to basically create a parallelized stochastic gradient descent. In particular, what's going to get parallelized is the gradient computation, right? Because if you think about the data set we have, it has 50,000 examples in it. And what we're going to do is split those examples across different engines. And so when you compute gradient, each one of the engines is going to do a gradient on a little sample on its own. And so we talked a little bit about that last time. And so the plan for today is to begin by answering your questions on homework 4. So over the last couple of lectures, a number of you have said, hey, lecture seems to be going a little too fast. I have like a hard time catching up. So the only way I can slow down is if you ask me questions. So I hope you've prepared some questions, and if you have some questions, we'll get to them at the beginning of class today. Then we're going to do the practice exam. So just out of curiosity, how many of you tried the practice exam? So maybe about half of you. So my plan is to actually do this in class. So I don't have to do this today. If you want to practice and do it on Thursday, I'll do it in class on Thursday. But I want to do it in class just to show you that it is possible to get this done in like the time period that we're talking about. And all of the exams, all the practice exams, I do before I give them to you, right? So I've actually programmed that. I have a reasonable understanding of how much time it took me and sort of a reasonable guess on how much time it should take you. And so if we're not going to do the practice exam today, then what we're going to spend most of the class doing is talking about networks and Pyomo. So we're going to introduce NetworkX, which is the main Python module for working with network data. And then Pyomo is the main module for writing linear and integer programs. And also it has other abilities, like you could do nonlinear programming in it as well. So Pyomo interfaces with all kinds of solvers like Gurobi, Cplex, and so forth. So knowing how to program in Pyomo should significantly increase your ability to do optimization in Python. Okay, so unless there's any questions about what the plan is for today, or any questions in general, yeah?
Do you have any practice examples for practicing writing fast?
I do have some other practice exams. So I could put up one more practice exam on Canvas if you like. Okay, yeah, so I'll do that after class today. So, but the one that we're going to do in class on Thursday is going to be the first one I put up, like the one about groups and reviews and so forth. Also, as a side note on that, I noticed that a number of you did the peer reviews on Canvas, and that's fantastic. I hope you found that helpful, and I'll keep doing that for the rest of the homework assignments. So you can take a look at some other people's code and see how it's similar or different than yours. Yeah.
When you're creating videos, we're explaining what, so for example, homework 3, that was a big homework. So what should we, what should we concentrate on saying in those videos?
So the TA tells me that those videos are tremendously helpful for him to understand your code. But what I would focus on is things that you think are unusual or the overall code organization so that he can know sort of which part of your code is doing what and how, like, what are some decisions that you made about implementing your code. So you don't have to go line by line, because one of the things that he's told me about is that some of the videos are too long, and when it's too long, it's not useful for him. And so sort of just kind of give a brief summary overview of your code to help him understand how everything is flowing together. Yeah.
You should put up the tier stuff for homework 3 within a time first to use it to help us with homework 4.
Yeah, absolutely. Yeah, I'll assign peer reviews maybe later this
Do you
evening.
have due dates for those? I know when you
So for homework 4, I do have a due date. I don't think I posted it on Canvas, but I did post it on the class calendar. And it's after the exam. So you have maybe 2 weeks or so to get that done. Maybe just under 2 weeks. Okay, other general questions before we go into your questions about homework 4. Yeah.
So, like, I have questions related to homework 3 actually. So, in your solution, sometimes you have used evaluate, and sometimes you have used stochastic evaluation of the function. So, like, did you have something specific in mind when you use?
Yeah. So in general, I would try to avoid using feval, and the reason is because on our
We haven't discussed like what exactly evaluation is there.
Oh, okay. So it's kind of the same as sgrad, right? So if the objective function is a sum of terms, I'm not going to evaluate all that sum. I'm going to sample a random subset and evaluate on that. So just to sort of give you an example, let's say that the objective is this. So let's say f of w is something like our sum from 1 to 50,000 of w minus xi squared. So this kind of looks like the first classifier that we're doing. And I didn't do the notation quite right, but it kind of looks like that, right? So one way that you might think of f is kind of like an average distance from the w's. So I could put a 1 over 50,000 at the beginning, right? And this doesn't change the optimization at all, because all I did was multiply the function by a constant. Like, nothing changed, right? So now I could say, like a stochastic f kind of looks like this. It's 1 over m, sum from I equals 1 to m, of norm w minus xi squared. So I'm going to pick just m examples and take the average of those instead of taking the average of all 50,000. So that's kind of what stochastic function evaluate in my code is doing. And the reason that in general I try to avoid it is because this is extremely expensive on the whole database of 50,000 examples. And in fact, sometimes, kind of depending on the way that I wrote the code, my laptop might even run out of memory. And so I would get an out-of-memory error in Python because of that. Other questions?
So, in your Python class, you use the take function, right?
Yep.
I could do it through the slice operator, so I didn't understand exactly why we had to use the take operator.
So I use take, but there's many different ways of doing things. So maybe the way that you did it works just as well,
So it
right?
was like just a simple slicing we would actually do. I didn't have to even reshape or do anything.
So I definitely use take for homework 4, and it's because if I have a bunch of w's, okay, so my w vector, what does it look like? What is a point? So in stochastic gradient descent, we're kind of going through these points, x0, x1, x2, and so forth, right? Like at each step we have one of these random points. What does one of these points looks like in homework 4? It looks like this. It looks like w0, w1, w2, up to w9, right? And each one of these is something like 784 coordinates long, right? So this whole thing, like each one of my x's is 10 times 784 coordinates, right? So I'm doing stochastic gradient descent like in this dimension. 10 times 784. Does that make sense?
So it actually, so you're basically vectorizing, right?
Yeah, so the reason that I need to do the take is because I need to take the right piece of X to kind of combine with the data over here.
But not all of them.
Yeah. Right? So because in general, and I can write the correct notation here, it was something like BK minus AK, right? Where a data point looks like AK, BK, where this is the category, and this is the image. Right, so I need to sort of take the right piece of X to put in there. Does that make sense? Okay, other questions? Yeah, back there.
Website says there's going to be project for the presentation from November 17th onwards. So I want to have classes or just support classes allocated for presentations.
Yeah, the whole class time from that time forward is going to be presentations. So we're going to have about 3 presentations per class period, between 2 and 3 presentations, and your presentations are going to be about a half hour long. And I'm going to give you some more information about that as we get closer to that date.
So based on that, how many more things like of homework assignments?
So after homework 4, we have 2 more homeworks. So just homework 5 and homework 6.
And are we expected to finish our project by the start of presentation?
No. So I'm gonna randomly assign groups in terms of presentation order. So some of you are gonna have to present a little early, but all of the projects are gonna be due at the same time at the end, right? So the groups that go towards the end are gonna have a little bit more time to work on their presentation. The groups that go in the beginning are gonna have some feedback from the class a little bit earlier and time to improve their projects by the due date.
So the presentation will be more about the idea and what we are going to do and not like...
Oh, no. You should definitely have something done by presentation time. Like,
Will it be more about, like, we might not have completed the whole thing, but like what we are...
well, as much as possible, right? And it's because we can't do the presentations, in parallel. So, like, some people are just going to have to work, like, in a more compressed time frame. Okay, other questions? Yes.
I'm just wondering that in your course, homework for homework 3, does your solution converge after 200 or 300 iterations?
So the question is, does the solution converge after 200 or 300 iterations in homework 3 or 4? So in general, it's really hard for stochastic gradient descent to know when it converged because it's random, right? So there are several things you can do. You can run it from many initial conditions to see if you get about the same end condition after that, and sort of compute variances on your result to see that the variance of the result is relatively small. So that's kind of one way that people prove that stochastic gradient descent converges. And it's something that I thought about giving you as a homework assignment, but it's sort of even more work on the same algorithm, so I decided not to. But if you wanted to check, what you would do is you would take your vectorized code, you would run something like 10,000 points on it, and then compute the variance of the results. And you could even plot a little confidence ellipse around it. So it'll tell you how converged a stochastic gradient descent is after that many iterations. Okay, other questions? Yeah.
Could you talk about organizing data, like you were drawing using the example, but like in the last homework in X, there's a time where there are 4 different points, and they each have their own set of tuples, and then the history is getting built sort of deeper.
Yeah.
When do you use like lists or arrays or tuples or matrices or that kind of thing?
Okay, so for the history, I use the collection. I use the, a queue. You could use a list. Some people in class use the list. I basically use an array when I'm going to use array operations, right? So when I'm going to be doing things like multiplying element-wise or adding element-wise, like all those SciPy operations that are super fast. If all I'm going to be doing is adding things to something and removing it, then some of the built-in Python data types are much, much faster than an array. And the reason is that an array has to be all next to each other in memory, while a queue, for example, does not. And a list in Python happens to be next to each other in memory, but in sort of like this weird optimized way. And it can turn out that it's generally more efficient to append to a list than it is to an array. All right, so one option I could do is something like a.append x, and another thing I could do is a equals scipy dot vstack a and x, right? Something like that, right? Because vstack's kind of like an append operation if you think about it. But this is much, much, much slower than this. And if your history size is like 5,000, this is roughly 5,000 times slower than that. Yes.
I had a question regarding importing. So, like I've seen, for certain import statements are like from collections, import something.
Yep.
So I tried, the object relation. So instead of writing this, if I write for example, instead of from collections import deck, I write the package name dot deck. It doesn't work, right?
Oh, you have to import collections then. Okay. So you have to import the package and then do collections dot deck. Yeah. Other questions? Yeah, back there.
So far we have used parabolic function, which has a nice name. If we have two minimum points, we have it close to the starting point, can converge to one minimum point.
Yeah. So the question is, what does stochastic gradient descent do when you have two minimum points, or a non-convex function in general? Yeah. So you can think of the function maybe being locally convex, and then you might converge to one of those points. But, in general, there's not really a proof of that. Like, you might sort of like bounce around in some odd way based on the shape of that function. That's also a possibility. So the proofs really are primarily for convex functions, where we know that we have a minimum. Other questions? Yeah.
Homework 3, I didn't understand the relative tolerance condition that you.
Okay, so the question is the relative tolerance condition for stopping in stochastic gradient descent. So let's say that this is my history in stochastic gradient descent, right? So I have a x here. So each one of these boxes is an x. And there were two parameters in there, and I forgot exactly what they were called, but one of them is something like window size. And what was the other one? W interval, right? Okay, so W size says how many points should I average to get a solution? And we know that in general we should be averaging points because it's a lot more stable than a single point in stochastic gradient descent, because those single points are bouncing around a lot, right? So here's, let's say W size is 4. So one solution I'm going to get from my latest 4 points, okay? But I want to, the entire idea behind that function is to check if my solution value is changing very much. And if it's not changing very much, then I'll say that the algorithm has converged. So that was one of your question, when does it converge? So one criteria might be that the objective function value isn't decreasing very much anymore, okay? So I'm going to get one solution here and check the objective function value here. So let's say that this is, let's call this objective nu, okay? So I need to compare it to some other previous objective function value, right? So one idea you might have is, why don't I take the previous 4 and compare it to the current 4? So why is that a bad idea? Because they're highly correlated, right? So stochastic gradient descent was bouncing around over here, so I don't want to compare sort of points that are right next to each other. And so instead of taking the previous 4, what I'm going to do is sort of space it out in terms of how far in between I take my two samples. And that spacing is going to be, this W interval times the W size. So that's how many sort of boxes I just skipped between the two samples. And then here I take another sample that's of W size, and let's say that this is objective old, right? And now the absolute tolerance just says, make sure that the difference between these is less than 1 times 10 to the minus 6. Or the relative tolerance is make sure that the ratio is almost 1, right? So I don't care which one's bigger, but when I figure out the ratio, it should be almost 1 to within 1 times 10 to the minus 6.
When you wrote the condition, you had some, you added 10 power minus 11 and subtracted 10 power minus 11.
Yeah, and that's just in case this objective is 0. So I don't want to divide by 0 when I'm computing that ratio.
But why did you add a third numerator?
It may have been a typo in my code as well, so that's also a possibility. But in general, yeah, because of the ratio taking, often in the denominator, you add some small number to make sure you're not dividing by 0. Okay, other questions? Yeah.
When your stochastic gradient descent converges, did you say the solution is the average of the last few points or the last point?
It's definitely not the last point. I would say it's the last quite a few points. So, and you could probably check this with your parabola code, which is if run it for like 20 steps or 30 steps, however many you want, and then check the objective function value at the last point versus the last 10 points versus the last 30 versus the last 50, and you'll see that there's sort of some area in between there where you're getting a decrease because of the averaging. And so for homework 4, I think I'm asking you to average something like the last 100 points. And the reason that I'm doing that is because look at this dimension here. Like the dimension is like about 7,000, right? So we're doing stochastic gradient descent in 7,000 dimensional space. And so it's like bouncing around in there quite a bit. And so we might need to average like a few of those points to get, something that's not, doesn't have a lot of variance in it. Other questions? Okay, so no questions on homework 4? Okay, fantastic. So good luck with the homework assignment. Bring some more questions next time. And I'll skip going over the practice exam because only a few of you have done it so far. And instead I want to talk about networks in Python. So the primary module for doing networks in Python is called NetworkX. So let's look it up. And the reason that we're going to talk about networks in particular is because it's an incredibly useful concept in terms of data and problems. Okay, so lots and lots of problems can be expressed in terms of network problems, and lots of data can be thought of as data points and relationships between them. And so whenever you have a problem where you have a data point and some relationship to other data points, you can conceptually think of that as a network. And so NetworkX is a general package for doing that, for storing such data. And you can sort of read the documentation yourself, and we're going to go through some examples shortly. Okay, so let's read what I'm doing here with NetworkX. So first, I'm importing the package, and then I want to define a network data type. But it turns out that mathematically and in terms of problems, there are several different kinds of networks, and each of them corresponds to a very different kind of data type. Okay, so here are some differences. So here's a network where there's direction to the edge, right? So I can go from A to B, but not from B to A. So oftentimes people call this a directed network. And it's called directed because the edges have a direction, okay? But an entirely different kind of network is one where the edges go both ways. And oftentimes people will draw this without arrows. So they'll just draw it like this. So an edge from A to B is the same as an edge from B to A, okay? So sometimes people call these as undirected. And so that's one major difference between different kinds of networks. And the next one is a graph or a multigraph. Okay, so in a multigraph, you can have two of the same edge present. So this is an edge from A to B, and this is a different edge that's also from A to B. Okay. And multigraphs can be directed or undirected. So here's an undirected multigraph. And in graphs, you can't repeat edges. Okay. Yeah.
How much more of the material that we're covering between on-test is going to be on-test?
So on the test is just going to be program something. But if your question is, am I going to ask you to program something in Network X or Pyomo? It's unlikely. It's unlikely, yeah. But pandas, SciPy, Matplotlib, all those things are perfectly, yeah. Okay, so let's import Network X. And here I'm going to create a graph data structure. So digraph means I'm creating a directed graph. So in a directed graph, the edges have direction, but I'm not allowed to have repetition. Okay? And just to show you that the various other objects exist, there's also a multi-digraph, so that means it's a multigraph that has directed edges. Yeah.
You said digraph doesn't allow repetition. What repetition are you talking about?
So if I put in edge AB twice, it's going to be the same edge. Yeah, and I'll show you in just a moment. So there's multigraph and multi-digraph, and then there's also graph that's undirected. So let's in this directed graph, let's add an edge A, B, okay? And then let's add it again. And then let's look at the edges. Okay, so I added it twice, but it's in the graph only once. And that's because directed graphs don't allow edge repetition, okay? Now let's create a directed multigraph, okay? And then in this directed multigraph, let's add edge AB, and let's add it again. And then let's take a look at the edges. Now it appears twice because it's a fundamentally different kind of object, right? So it has different operations. In a digraph, if I add the same edge twice, it won't take it. In a multigraph, if I add the same edge twice, it will actually take it, okay?
Can I know whether it is a direct or indirect from the result?
From which result?
This.
As you as a programmer decide what kind of object it is, okay? So you decided when you created, so right here when I created this object, I decided I wanted to store multi-directed data, okay? But for some other programming project, you might decide that's not really the data that I want just the graph data, okay? So just from the list of edges, you may or may not be able to, yeah.
edges will have properties, right? Some properties.
Yeah,
Like
yeah, so we're going to talk about that.
In case of diagraph, will like adding another edge twice, replace it with a new property that we added?
Yeah, I'll show you how to store edge properties in just a moment. Okay, so let's go back to our directed graph. So we can take a look at its nodes, and we can take a look at its edges. And so what's the difference here? So how come when I called the directed graph.nodes, I got this, and when I called the directed graph.edges, I got that? Yeah, edges are pairs of nodes. And not only that, they're directed pairs of nodes. So it really matters which one's first. So this means it's an edge that starts at A and is going to B. Okay, so let's add some data on the edges, okay? So you can do that with things like this. So I'm going to call add edge. And before I had just edge AB, but now I'm going to add edge BA. And I can throw in just like arbitrary data on this edge, okay? So I picked the word length and assigned it the value 7. I picked the word name and assigned it the value Fred, okay? So let's execute this and see what happens.
Those just arbitrary names called like QTX and your keywords in it.
Say again?
Those just arbitrary like length and name, like you can put anything.
Yeah, absolutely, and you'll see how they show up in just a moment. So let's take a look at edges, and let's write data equals true. So when I wrote edges before, I just wanted what are the edges, but now I want the edges and their associated data. So let's see how that's going to show up. So I have two edges that I added. One was AB, and it had no data in it, right? Which shows up as this empty dictionary here. And the other was BA, and it had a bunch of data in it, and it showed up as key value pairs in this dictionary. So that's why I can make up whatever I want for that data, because it just basically turns into a key to a data dictionary that goes on the edge. Does that make sense? So there's several ways to access that data. So this is one. Another way to access that data is to go to edge B A, and then I get that dictionary. Does that make sense? So I could do something like go to the dictionary of edge AB, which is currently empty, and set that node's name to Joe. And now when I look at edges with data equals true, I actually have a piece of data on edge AB. Does that make sense? Okay, fantastic. So we can put data on edges, but just as much as typically you want to associate data with edges, you also typically want to associate data with nodes, okay? And the way that works is the same. You can add node, C with some data on it. And I could look at nodes, data equals true. And A doesn't have any data with it, B doesn't have any data with it, but C has a dictionary where Fred is associated with 7. Okay? And similarly, the way that I access the edge dictionaries directly, so this was me accessing the edge dictionary directly, I can access the node dictionaries directly. So just by doing node C, so that's the node dictionary for node C directly, and this is the node dictionary for node A directly. Make sense? So basically the same thing going on here, right? So we just went over how to add a node and take a look at the node data, and also access the node and edge dictionaries directly. Okay, so yeah.
So here we have used string, for the dictionary key. Now, string is immutable in Python, but if we use, say, an integer, we can use integer.
Oh yeah, because it's just a dictionary key. Yeah.
So, say when we are creating edges, since like in string we had a and b as immutable, then when we created a new edge b from b to a, then it was exactly the same b as the earlier b, right?
Yeah.
But what happens if the key we use is an integer?
Oh, so in other words, you want to do something like you want to add an edge. You want to like 2 to a, something like that, right? Okay, what that's going to create.
Yeah, but now if you say like from.
That's right, because what NetworkX does is it takes whatever you passed in here, and it uses it basically like a dictionary key, right? So this is not the second node. This is a node whose name is the integer 2. The same way that this is a node whose name is the string b.
No, so what I was trying to ask is like 2 is not an immutable object, right, as such. So now when I add another edge, say from C to 2,
Okay.
are those two the same?
Yeah, absolutely. Yeah. Yeah. So if you add edge, so let's add that edge. And now let's take a look at the nodes and the edges. Yeah, so that too is the same. And the reason is because hash of 2 always evaluates to the same thing. Okay, the same way that hash of b is going to always evaluate to the same thing. Okay, so that's kind of basically how Python figures out whether 2 things are the same or not in this particular case.
So when you add properties for the age, you add like length and name. I know this should be the default properties. But when you add to the node, you actually add some breadth.
Yeah, length and name are strings that I just made up. Like I could have used anything. Yeah.
It's not.
No, it's not default. I could have used anything.
Okay.
Yeah. Yeah.
Is there any way you can find the edge or the node by attribute, like the name or like the
So you want to find which node has.
name, like spread or something?
Unfortunately, not. So that's a great question. So the question is, can in NetworkX we find all the edges whose length is 5, for example, right? So unfortunately not. And that's maybe something that's going to get fixed in the future. It's not clear. However, one thing that it is very useful for is successors. So I could find all the successor nodes of A really quickly. So I could say like, give me all the edges that go out of A and the name of the nodes that come after that. So those of you who've taken networks class with me, you know that this is an extremely useful operation, and it's implemented very, very quickly in NetworkX. So that allows NetworkX to do certain graph algorithms very quickly. Okay. So I'm going to skip this example, but let's just talk about it quickly without me executing it. So here I create a graph. Okay, so not a digraph, it's a graph. And I add edge AB with length 12, and I add edge BA with length 18, and then I print out edges data equals true. What am I going to get on this printout? That's right. I'm going to get only a single edge AB, and its length is going to be equal to 18 because it got overwritten right here. In an undirected graph, these two are the same edge. So essentially what I was doing here was just rewriting the length property of the first edge I created. Okay, so let's kind of create a small example here. So it's a directed graph. We're going to add an edge from A to B, whose length is going to be 2. We're going to add an edge from A to C, whose length is going to be 9. and we're going to add an edge from B to C whose length is going to be 1, okay? And successors of A, we already saw what that does. So can somebody tell me what predecessors of C should return? A and B, right? So those are, give me all the nodes who have edges pointing into this current node. So let's execute that really quickly. Yep, A and B. There's tons of useful functions on these network objects, right? I'm not going through all of them, but here are 30 different functions you can do on these network objects. For example, a useful one might be reverse. So what does that do? It takes all the edges and flips them around, right? So various other interesting things like find the degree of a node, return the adjacency matrix of this graph, whether a node has a predecessor or has a successor, the in and out degree of the various nodes, and so forth.
The GD was a graph, right?
It was a directed graph right here. Yeah, it was a directed graph. Okay, so the other thing that I'd like to highlight is that NetworkX has a tremendous amount of built-in algorithms to compute things with networks. So one of the things that we're going to do an assignment on, maybe your next assignment, is going to be just computing shortest paths. So you're basically going to do the equivalent of a little TomTom or something, where we're going to take in all the geographic data for Austin streets. I'm going to give you a couple of lat-long coordinates, and you're going to compute a route using that map. That's the shortest route from the origin to the destination. And maybe we'll do some variants of that. So to do that, you need an algorithm to compute shortest paths. And NetworkX has a bunch of built-in algorithms. And you can take a look at them by just looking at NetworkX algorithms. And there's just a lot of them here, okay? And so most of the time, if you're looking to do something with a network, it might already be implemented in NetworkX, okay? So it's worth reading through that. But just to play around with it a little bit, let's just compute the shortest path length from A to C. So in our graph, when I compute the shortest path length from A to C, what should I get? 3, right? Okay, so let's see if we actually get that. Okay, so the reason, so there's a reason for this. Let's take a look at the documentation for shortest path length. So I expected 3, but I got 1. So let's go back and read the documentation. So compute the shortest path length in the graph. So you pass in a source, you pass in a target, and you pass in weight, which is none or string. If none, every edge has weight, distance, cost equal to 1. If it's a string, use this edge attribute as the edge weight. So why did shortest path length from A to C return 1? Yeah, because it's not using the lengths, right? It's just using the number of edges. And then it actually is 1, because it's just going A to C directly, right? So I should be able to go back here and pass in length, and then I get the 3 that I was expecting. But in addition to looking at the lengths, I might want to compute the what the actual path is. Okay, so let's do the same thing, but instead of calling shortest path length, I'll call shortest path, and then I actually get the path ABC. And some other useful things are you could look at. So let's take a look at NetworkX dot shortest path so the source is optional, but so is the target. Okay, if not specified, compute the shortest paths using all nodes as the target nodes. So what I could do is this, and now it's computing the shortest path from A to every other node in the network. So for those of you that have learned Dijkstra's algorithm before, you know that this takes as much time as that. So if you want the shortest path from A to every other node, it's just as fast to do this as it is to do a single call of that. So here I'm getting all the shortest paths. So the shortest path from A to A is to just do nothing. The shortest path from A to B is to go from A to B. And the shortest path from A to C is to go A, B, C. Okay? Okay, so fantastic. So now you know how to create some network data structures and associate some data with edges and nodes and do things like compute shortest paths. But the next thing I'd like to teach you is how to implement a linear program in Python. And a great example of that is going to be a shortest path linear program. Okay. So the same thing that is implemented in NetworkX using Dijkstra's algorithm, we're going to implement using linear programming and Pyomo. So to do that, I have to introduce you a little bit to the shortest path linear program. Okay, so the idea here is the following. I'm going to introduce some variables, which are going to be yij, and they're going to be either 0 or 1. Let's say, do I take edge ij on the path from S to T? So let's say that there are two nodes S and T that somebody has given to me, and I want to find the shortest path from S to T. I'm going to associate a variable with each of the edges that's either 0 or 1, and the variable is going to be 0 if the edge is not on the path, and it's going to be 1 if the edge is on the path. Okay? So those are going to be my variables, and I'm also going to have some data. And my data is going to be Cij, which is going to be the length of edge ij. Okay? So given this, can somebody help me write down what the objective function for this optimization problem is? So if I have these y variables, I've defined them, they're going to be 1 only on the shortest path, I have this data, the c's, what's the objective function for shortest path using these definitions? Yeah. Yeah, so I think many of you had it. So what you're saying is something like this. Take the c's and multiply them by the y's, right? So now I'm only going to be taking in the lengths that are associated with the shortest path. And this is going to be summed over all ij that are in the edges. So my graph here is a bunch of vertices and a bunch of edges. And what I want to do is minimize this over the y's, okay? So I'm going to write down now a bunch of constraints, because right now, if I just go and put this into Cplex or an optimization solver, and let's say that I have constraints that look like, well, let's say that I have these constraints, that yij is in 0, 1, okay? So if I just go and put this into an optimization solver, what kind of answer am I going to get? 0, right? So I need to somehow force the y's to make a path from S to T. So I'm going to write down some constraints that do that, and then we'll talk about why they do that. So here it is. So these are edges. I'm summing over edges. So this is for S, this one's for T. This is for all nodes A that are in the vertex, and A is not equal to S, and A is not equal to T. Okay, and here's maybe a picture that's going to help. So here is node S, and I have a bunch of edges that are coming into it, and a bunch of edges that are going out of it. So each of these edges has a Y associated with it, and each of these edges has a Y associated with it. Okay, so what is in this first sum? It's all the Y's for incoming edges. Okay, so I'm summing all the Y's for incoming edges. And what's in the second sum? All the Y's for the outgoing edges. Okay, and it says that this difference has to be -1. So what does that say? Yeah, there has to be like one more thing leaving S than is entering S. Okay. So similarly, what's going on with this T equation? What's the first sum here? Everything going into T, right? The second sum is everything going out of T, and I want that difference to be 1. So over there, what am I saying? Yeah, there's one more incoming than there's outgoing. And then for the rest, for all the other nodes, whatever comes in has to equal to whatever goes out. Okay? So what is this doing? So let's just kind of think about it conceptually before we go to program it. So let's say that here is S and here is T. And originally, if I didn't have all these constraints, the answer that you were going to get is 0, right? That's going to now be infeasible because I have to have one more thing going out of S than otherwise, right? Okay, so let's go and make something that's going out of S be 1. Okay, so I picked this edge to be 1. But now what's going to happen? At this node, it's going to be infeasible because I have 1 coming in and 0 going out, right? So I have to go to that node and make that feasible. And maybe I pick this edge so that everything is balanced there. We have the same amount of things coming in as are going out, right? And I could do that here, and I could do that here. And the only way that this is going to stop is if I connect to T, right? Because the only node that can have one more thing going into it than going out of it is T. Does that make sense? So that's why these inequalities, or these equalities, force us to pick a path of Y's from S to T, okay? So some questions for you. How many equalities are there? So there's many equalities as there are nodes. And there's as many Y's as there are edges, right? So there's one equality for S, one equality for T, and one equality for every node that's not S and not T. Okay, so all of them, like every node has an equality. So this is how to write shortest path as a linear program. And it turns out that this, you can replace it with just Yij bigger than or equal to 0. And it turns out that regardless if you have the integer constraint here or the just positive constraint, you're going to get the same answer in both cases. Okay, and that's just because of some special structure in this linear program. But before we go and we program this, I just want to tell you about one short generalization, which is that this right here, in shortest path, we've just had -1 where we want to start, a 1 where we want to end, and 0 everywhere else. In general, you could think of this as a node imbalance. Which basically says how many more things can I have coming into this node versus going out of it. And so I might have lots of node imbalances around the graph, not just one for leaving and one for coming in. I might have sort of a bunch leaving, a bunch going in, And what this linear program is going to do is make sure to match all those up at minimum cost. Okay, does that make sense? And the reason that I do that is because when we go and reprogram this, we're going to program this more general version. So we're going to have a node imbalance at all the nodes, as opposed to just a single S and a single T that we pick to go between. So a little bit of terminology in case you run into it. Sometimes people call this the network flow equations. And that's because we're thinking about the flow at each node. It's like how many Y's are coming in, how many Y's are going out, and that has to be equal to the imbalance, which is a given constant. Okay? So let's take a look at what some data for a problem like this might look like. Okay, so one of you told me how to make this bigger font last time. What do I do again? This thing? Okay, great. And then let me also open up the arcs file. Okay, so in general, this is how you might store graph data as a CSV file, right? So I showed you how to store it in NetworkX, and this is how you might store it as a CSV file and then use pandas for all kinds of operations, right? So in a node CSV, you might want the node names, which are going to be here, so A, B, C, D, E. And then you might want a bunch of data associated with each of those nodes, right? So all of that data is going to be extra columns that come after the node name. So here I have, data, data2, and then the node imbalance, which for us is going to be like shortest path. So we're going to have 1, -1, and 1, 1. So in this problem, what's the start node that I'm going from? A. And where am I going to? E. Okay. Now let's take a look at the arcs file. So it's also going to look really similar, okay? So an arc is going to have a start node and an end node, and then I might have a whole bunch of data associated with each of the arcs. So all of that extra data shows up as columns here in my CSV file. So here I have an arc from A to B, and its data is going to be 1. One from B to C, and its data is going to be 1. One from C to D, and its data is going to be 1, and so forth. So let's maybe spend just a little bit of time drawing this so that we can get an idea of what the solution should look like if we actually solve shortest path on this graph. So here we have nodes A, B, C, and D, and E. And the data was all ones from A to B, B to C, and so forth. So let's draw that. A to B, B to C, C to D, D to E. So this was just length 1. And then A to C was 3. A to D is 4. And A to E is 5. Okay. So, and the node imbalances were -1 at A and 1 at E, and there's zeros at all the other nodes, right? So, what's the solution I should be getting here? Yeah, so that should be my shortest route. So I should be getting Y's that are 1s over here and zeros everywhere else. Okay, so let's see how to actually go about programming this very general linear program in Python. Okay, and we're going to do it in a general sense in the following, that if you want a different graph, all you have to do is change the CSV files and execute the same code and it's going to solve shortest path on that new graph. And to do that, I want to introduce you to our next module that's going to be important. So it's called Pyomo. So you can read the Pyomo documentations and examples online. They're quite useful. But just to put it in context, this is the general structure of how optimization software works. So often there's something called a modeling language. And then there's a solver. So the modeling language allows you to describe what the problem is. So it describes the variables, it describes the data, it describes the inequalities, the objective function, whether you're maximizing, minimizing, and so forth. So Pyomo kind of falls in here. But there are all kinds of other modeling languages. For example, there's GAMS, there's AMPLE, and lots of other modeling languages exist. And then there's the solver that actually takes that description from the modeling language and then implements various optimization algorithms, not stochastic gradient descent, but things like the simplex algorithm or a barrier method or network simplex that's going to actually return solutions to that particular optimization problem. So lots and lots of solvers. So Cplex is maybe one that you've heard of. There's Gurobi. There's GLPK. And there's tons and tons of other ones here, like MOSEC, IPOpt. Yeah, Express, so forth, right? And each of these solvers kind of tend to be slightly better maybe in some situations than others, okay? But what a modeling language does is it allows you to interface with any of these solvers. So I can write my program once in Pyomo and then try to solve my problem in Cplex, and if it doesn't work, try to switch the solver to Gurobi and see if it does something different. Or try to switch the solver to GLPK and see if that does something different, okay? So let's see how we can express this problem in Pyomo. And the basic parts of a problem like this are these. There's variables, there's data, there's an objective. So let me kind of write these. There's variables, there's data, there's an objective, there's constraints, and quite often there's something called sets. So sets and data, you can think of roughly the same thing. But what sets allow us to do is kind of decide what we're going to be summing over, right? So here we're summing over the set of edges, and here we're summing over the set of nodes, basically, or we have one of these equality constraints for every node. And so for this network problem, what might you guess are the two important sets? Say again? Yeah, edges and nodes. Like those are going to be my two important sets. And what are the important pieces of data? The length, absolutely. So there's going to be one piece of data on each edge. And the imbalance. And there's going to be one piece of data on each node. Okay? Okay, so let's see how to program this in Pyomo. And I'll post this online. This is a fully written example that executes here. So it turns out that I don't actually need all of these imports. I think I could get away with just this bottom one. Okay. So what we're doing here is importing the Pyomo environment. So I told you not to do things like import NumPy as NP. But in this particular case, the reason I'm doing it is because this is extremely long to write. And so when it gets to sort of like very long sequence of modules, then I do tend to shorten it to something. So Pyomo environ, I just import as PE. And then I'm going to import pandas because I need to read in those CSV files that are going to define my node sets and the various data associated with them. Okay. So I've created a class that's going to be my shortest path class. So this class is going to solve problems like the shortest path problem with various data. And this class takes in two files, a nodes file and an arcs file. Okay, so those are going to be like the two CSVs that define the node imbalances and then the distances for all the edges. So let's read. Let's see what these first few lines are doing. So it's reading in the nodes file, and you're quite familiar with the first line here. So node data is pandas read CSV, node CSV. But you might not be familiar with the next two lines. So let's execute those in an interpreter to see what's actually happening there. So I'm going to import pandas. And then I just want to say node data equals this. And then I want to say node data set index node. But before I do this next line, let's take a look at node data. Okay, so it looks like a pandas data frame. And this is the auto-generated index of the data frame, okay? So this is the row at index 0. This is the row at index 1, the row at index 2, and so forth. And node is a column in this data frame, okay? But when I execute set index, what I'm telling pandas is forget this auto-generated index, okay? I have a column that I actually want to use as the index. Like, I don't want you to use your auto-generated thing. So now, and of course I say in place equals true because I actually want to change that data frame instead of create a new one. So now if I take a look at node data, it no longer has that auto-generated index, okay? Now it has node A, so this is the row at position A, the row at position B, the row at position C, and so forth. Okay? Yeah.
So if we put in place equals to false, it will just create a copy of ABCD and so.
That's right. That's right. So if you don't have in place equals true, it's not going to change that data structure. It's going to return a copy of it. Exactly. So let's take a look at the next line. Sort index. So in this particular case, I had written the CSV file in a nice way, okay? I had written the CSV file so that it was already in a sorted order. But if it wasn't in a sorted order, this would have sorted it all out. So that it'll give me sort of a nice legible order that I can search for things in, okay? So let's see what happens with arc data, which kind of looks pretty much the same. So I'm going to read in the arc data. But now notice that when I do set index, I'm going to pass in two columns. Okay, so arc data, when I write it in, has this auto-generated index. And then it has start, end, and arc data. But now when I do set index, I'm passing in two columns to set the index. So why didn't I just pass in start? It's not unique, right? I need a unique index for each row. And because it's an arc data, the start and the end is going to be something unique. And as you can see, this already kind of limits my code to look at just directed graphs. Like, I'm not going to do directed multigraphs, just directed graphs, okay? So now if I look at arc data,
Wait, so if you put in AB and add another arc data, like another AB and add another arc data, would it?
it might give you an error. Yeah, it might sort of tell you that it's not a unique index, so you can't do that. And we can try to create a bug like that and see what happens. So let's take a look at arc data. So now you can see this is my index start end, but it's not sorted in a nice way. In particular, like here's a node, here's a bunch of edges that are coming out of A, and here's some more edges that are coming out of A. And so it's kind of hard for me to search for all the edges that are coming out of A, right? So now if I do sort index and I look at arc data, now it's sorted like in a nice kind of format. I can look at all the things that are coming out of A, all the things that are coming out of B, C, and so forth. Make sense?
So this sort will first sort for the start.
That's right.
Then for the end.
That's right. And the reason is because that's the index I created. If my index was end then start, then it would sort the other way. Does that make sense? Okay, so now I have these two data frames. And now I need to create the sets that are going to be the key part of me creating the linear program. So I need to figure out what are all the nodes and what are all the edges. So how am I going to figure out the nodes? I'm going to look at this data frame. I'm going to look at its index and give me all the unique things out of there. Same for the data. Look at the index and give me all the unique things out of there. So let's see what that returns. So if I do something like arc data index unique, it's going to give me all the arcs that are in the graph. Okay? Okay, so at this point, I'm going to create a different function, I'm going to call a different function create model that's going to actually use all the Pyomo tools to create that linear program. Okay, so let's read create model. The first thing that it's going to do is going to create a concrete model object. Okay, so this is just something that's built into Python, into Pyomo, and that's what we're going to use to describe objectives, variables, constraints, and so forth. Okay, but right now it's totally empty. It has no objective, no variables, nothing. The first thing that we need to do is create the sets that are going to go on this model object. And as you told me, the two important sets here was the node set and the arc set. Okay, so I'm going to create the node set, and it's going to be a set object in Pyomo, and I'm going to give it, it's a set object, but I need to tell it what actual value that set should have, okay? And the values that I'm going to give to it are from that pandas data frame that we got. So this Pyomo object now is going to be initialized with all the nodes that we read in from the data frame. And similarly with the arc set, except the difference here is that I need to tell it that it's a two-dimensional set because it has a start node and an end node. So each one of these pairs isn't an object within itself. It has like a first part and a second part. So that's what dimension equals 2 means over there. Okay? So that creates the node set and the arc set for describing our linear program. So now we have to create the variables. Okay? And I could have called these variables whatever I wanted, but I picked y because it matches well with what I wrote previously on the board. Okay, so I'm going to create these y variables. And how many variables are there going to be? There's going to be one variable for each edge, right? And that's what's happening here. It's saying create one of these for each arc in the arc set. And by saying domain, I'm basically restricting these variables, right? So here I'm saying they have to be non-negative. There's also a restriction .binary that's going to tell Pyomo that they're 0, 1. But because non-negative and binary returns the same answer in this particular case, I'm just going to say non-negative, okay? So now I've created the sets and I've created y variables that go along with those sets.
So if we pass some negative numbers, will it return the absolute value or return?
For which?
For this PE dot.
Here?
No, I mean the previous.
Sorry. Say again?
Self.m.arc set. If there is some, it's just the same line. Yeah, I mean for this, here, if there is some negative value, so we'll just raise an arrow or return the app.
No, because this is just a set. So imagine that I've named all the arcs. Like this is the first arc, this is the second arc, this is the third arc, this is the -3 arc, right? It's a set of arcs. And here I'm creating a variable for each of those arcs. So that variable doesn't have a value yet, right? So it's not like I've assigned it to 0 or 1. It doesn't have like a real number value. All I've done is I've created a Python object that's going to be a variable. I haven't solved anything yet, okay? So this is maybe a reasonable time to end, and we'll pick up with a little bit of review next time and finish discussing how to write this linear program in PyOmo. So thanks a lot for listening, and I'll see you all next time.